Okay, so let's get started. Last time we proved this theorem, the Check-Durham isomorphism. Okay, so we showed that if U is a good cover of a manifold, then Durham cohomology can be computed as the check cohomology of the good cover. Now, this means that Durham cohomology really doesn't depend on differential forms. It only depends on how the open sets intersect in a good cover. Okay, so for example, when you have a circle, okay, with these three open sets, you can represent that by a graph. So to each open set, you associate a vertex. And then if two open sets intersect, then you put an edge between the two vertices. Okay? So this good cover will be represented by this triangle. And the Durham cohomology of the circle only depends on this triangle. And that means any two manifolds with the same graph will have the same Durham cohomology. This is quite an amazing fact. Okay? So this graph is called the nerve of the good cover. Yeah, you need a good cover because when you have a good cover, you know that the intersection is always, diffeomorphic to Rn. So, like whenever you have an edge, you know that that represents an Rn. Now, in higher dimensions, then you'll have a higher dimensional graph, and that's called a simplicial complex. You have vertices, edges, and faces, in all dimensions. And the Durham cohomology depends only on that simplicial complex. So that's a consequence of the Check-Durham isomorphism. We proved that it's a linear isomorphism. But actually, Durham cohomology has a product given by the wedge product. So what we're going to do today is we're going to introduce a product on check cohomology and then show that this is actually an algebra isomorphism. Okay? All right. So now before I do that, so I'm just going to say something general about products on a differential complex. Okay. So let K with the differential D be a differential complex. Now, if you have a differential complex, then it's graded, right? and D increases the grading by 1. No, K goes from 0 to infinity. Okay, to be a differential complex just means that D squared is 0. That allows you to define cohomology. Now, what is a product? Well, a product takes two elements, and gives you a third element. And, it has to be linear in each argument. So a product is just a bilinear map. Mu from K cross K to K. And, because we're graded, so, it should take an element of degree A and an element of degree B and give you an element of degree A plus B, okay? For all A, B. So that's a product. Now suppose you have a product on a differential complex, and I'm going to write the product just as A dot B or as AB, okay? So if D, the differential, is an anti-derivation, with respect to the product, that means D of AB is dAB plus -1 to the degree of A, ADB. Okay, so if you have an anti-derivation, then there are a few obvious facts. Then, one, you know that a cocycle times a cocycle is a cocycle, right? Okay, because if A and B are cocycles, then dA is 0, dB is 0, then D of the product is 0. Okay, so the product of two cocycles is a cocycle, and then a cocycle times a coboundary. What should that be? Coboundary, yeah. Because like if, let me see. So if A is a cocycle and B is a coboundary, now if A is a cocycle, just a minute. Yeah, dA is 0. Yeah. So like let's say yeah, so like let's say you have C, okay? C is a coboundary, right? So, and let's say A is a cocycle. So you have a co-cycle times a co-boundary here. But A is a co-cycle, this disappears. Oh yeah, right. So this says a co-cycle times a co-boundary is a co-boundary. Right? Yeah. Yeah. Co-boundary. Huh? And then it goes the other way too. So a co-boundary times co-cycle is a co-cycle. Okay? Yeah. And so let Z of K be the co-cycles in K and B of K be the co-boundaries in K. Okay? Right. Uh-huh. Yeah. So K is a vector space, so it's got addition. Okay? And now you have a product on it. Huh? So if you have a product on a vector space, then that's an algebra. And so an algebra is also a ring, that has scalar multiplication. Okay. Okay, so what does this fact say? Fact one, what does it say about Z? Hmm? Yeah, it's closed under multiplication. Yeah. And obviously it's closed under addition too. So it's a ring. Okay. So one says that Z of K is a ring. And what does two say? A co-boundary times a co-cycle is a co-boundary. In terms of algebra, B of K is whenever you multiply something here by an element of the ring, you get back something in here. It's an ideal, okay? And it's a two-sided ideal because you can multiply on either side. So is a two-sided ideal in Z of K. Okay? Oh, sorry, here, gosh, yeah. This should be co-boundary. Uh, thank you for pointing it out. Yeah, and okay, so that means that the product, okay, so the product, it takes co-cycle and co-cycle to a co-cycle. It induces a map on the quotient. You can quotient out by BK. Because something in BK times something here will end up, in BK. And this is cohomology. Okay. So the upshot is that if you have an anti-derivation with respect to the product, then the product induces a product in cohomology. Okay? Yeah. So whenever you have an anti-derivation, so whenever D is an anti-derivation, with respect to the product, then there is a product. Then mu induces, this is a product on K, then mu induces a product on cohomology. Usually we put a star here. Cohomology. Okay? Yeah. So to get a product on cohomology, you just have to define a product on the differential complex, and then hope that your differential is an anti-derivation. Right? Yeah. Okay. So let's now define a product on the Czech-Dram complex, okay, on the double complex. And that will give us a product on the cohomology of the double complex. Okay. All right. All right. So this product, it should take P, CP, U, omega Q, and something in CRU, omega S, 2. Okay. The horizontal degree should add and the vertical degree should add. Right? Yeah. All right. So that means you take something here and something here, and you get something here. Oh. Yeah. I'm going to indicate this product by a little cup. It's called the cup product. Okay? Now, an element here, what does that mean? It means it's a Q plus S form on all the P plus R plus 1 fold intersections. So, so you need to give the form on this intersection, right? The intersection of P plus R plus 1 open sets. Okay. And let's see. And then omega is on P plus 1 open sets. Oh, sorry. Yeah, I want to define the product, right? Product. Okay, I need this component of the cup product. Okay, and now omega it Okay, it's got p+1 subscripts. And tall needs r+1 subscript. Tall. So you want to take the back r+1 subscript, and that means you have to start with alpha p to alpha p plus r. Okay? That way you have r+1 subscripts. Okay? And so you see that you have to repeat one of the subscripts. Okay? Now, when you define this cup product, you notice that you start with PQRS, but you end up with PRQS. Okay? That means you have switched the order of Q and R. And it's a general rule that whenever you switch 2 degrees, then you have to introduce a sign which is -1 to the product of the degrees that you switch. So this is the definition of the cup product. Without this sign, nothing works. With this sign, then you find that big D, big D is D prime plus D double prime, right? But I'm going to write D prime always as delta. So big D is an antiderivation. With respect to the cup product. Okay? And that means, well, you know what it means. And delta is also an antiderivation. Okay? I'm going to write that down because you might wonder, like, in this case, what is the degree? Eh? Because is it the p, because delta only changes the p degree, right? So is it just the p degree of omega? But it's actually the total degree. So delta omega, delta of the product is delta omega cup tall plus -1 to the degree of omega, omega cup delta tall. And the degree of omega in all cases is P plus Q. Okay? And the same is true of D double prime. So D double prime is actually -1 times little d. So, oh, I probably shouldn't be wearing the mask. Okay, I think it's clearer if I don't wear the mask. Yeah, so, these are what you want, right? You want the differentials to be antiderivations. And it's just like, a long calculation, but a routine calculation. And it works only if you have this sign. If you don't have the sign, it doesn't work. I don't quite know why. I don't know why whenever you switch 2 degrees, you have to introduce that sign. You know, there's probably an explanation for that. Maybe you'll find it on the internet if you Google it. Yeah. Yeah, it's rather curious to me that in graded mathematics, you always have that sign. Okay, yeah. So that means now you have a product on the cohomology of the double complex with respect to big D, okay? And now let's look at what this product looks like on the 0th row and the 0th column. Let me see. Oh no, on the augmented, on the new row. Yeah, so I have to draw it bigger. Yeah, so let's say here is C0 U omega Q, right? And that's a Q form on each open set of the cover. And then when we augment the double complex, what do we put here? Yes, so, say it louder. How do you augment this double complex? Yeah, the kernel of this difference map. The difference map says that the difference of a form on U and a form on V is 0. So that means the form on U agrees with the form on V. So it's going to piece together to give you a global form. So here it's a global form. Okay. Yeah. So that is the the augmented column, the new column. And so let's look at the cup product on this column. So the cup product on C0 U omega Q cross C0 U omega R is going to go to C0 U omega Q plus R. Okay. Okay, and this is an inclusion, right? Yeah. So now the cup product, is closed on this 0th column, and it restricts, right, to this new column. So this restricts to cup product on omega Q N cross omega RM. If you multiply two global forms, goes to omega Q plus RM. And what is it? So omega cup tall. Now P is 0, so you have only one subscript. P and R are both 0, right? So it's just this on alpha 0 is equal to, okay, P is 0, so it's just omega alpha 0. And then Oh, yes, here. I should put a wedge here, right? These are forms. So to multiply forms, you need a wedge. Wedge for alpha 0. And then what is the sign? The sign is -1 to the q. Just a minute. Oh gosh, this should be S, because R is 0. This should be S. Okay. -1 to the QR, but R is 0, so it's Q times 0. Okay, so it's just 0. So there's no sign. It's just omega alpha 0, which tau alpha 0. Okay. So you see that the cup product restricts to the wedge product on this column. Okay. Yeah. All right. So thus, as the cup product restricts to the wedge product, the cup product, oh, yeah. Uh-huh. Um, the cup product, just a minute. No, I don't think, no, I don't think I even want to look at this, right? Yeah, I think I just want to look at what the cup product is on the 0th column. The cup product on the 0th column, it means you need the form on each open set. Yeah, yeah, yeah. Yeah, so all I want to say is that the cup product is the wedge product on the 0th column. The cup product is the wedge product. But when I augment, with the double complex with this new column, the new column is the de Rham complex, and its product is also the wedge product. So what that says is that this map, which is the restriction map to each open set, it is an algebra homomorphism. Because you have the wedge product here, and when it comes into the 0th column, it's also the wedge product. Yeah. So yeah, it's a ring homomorphism, okay, and an algebra homomorphism, and so R that goes from omega star m into C0 of U omega star is an algebra homomorphism, and this goes inside the double complex. And that's just a subring of this, and so therefore, if you omit this, you go from here to here. That's a algebra homomorphism. Mhm. And mhm. And because um, D, uh-huh, yes, so it's an algebra homomorphism, and it commutes with the differential. Uh-huh. Yeah, so the induced map and the induced map in cohomology okay, so H big D of this complex, right? If you have an algebra homomorphism on the cocycles, the induced map will be an algebra homomorphism. Well, but we already know that it's a linear isomorphism. So it's a linear isomorphism that preserves the product. Therefore, it's an algebra isomorphism. Eh? Yeah. Yeah, so this isomorphism, it's what we call the generalized Mayavi-Torres principle. And now we know that it's not just a linear isomorphism, but it's an algebra isomorphism because we have a product now on the double complex. Okay, but we still don't have a product on check cohomology. So now let's look at the cup product on the bottom row. On the 0th row. Okay. So the 0th row is C0 U omega 0 C0 U, no, C1 U omega 0 C2 U omega 0. Okay. And we augment it by the kernel. Of this D. And that we know it's locally constant functions on open sets. Okay, so delta, it's just the alternating difference. Okay, so if you take alternating difference of locally constant functions, it will still be locally constant. Okay, so delta will restrict to delta on the check complex. And the cup product on 0th row, so restricts to this new row, which is C star U R. Okay. And so if you take, say, omega in CPUR and Paul in CRUR, then the cup product, it will be in CP plus R, UR, okay? It will be given by, I need alpha 0 to alpha P plus R indices, and it will be omega alpha 0 to alpha P times, now here you're just multiplying locally constant functions, so it's just the product of real numbers. And then the sign is -1 to the, well, Q is 0, right? So 0 times R. So, yeah, so that sign will disappear. There's no sign, okay? And so this, the cup product on the double complex will restrict to a cup product on the check complex. And then because delta is an anti-derivation with respect to the cup product, it will induce the cup product in cohomology, okay? Yeah. Yes, let's see. All right. So now we have a product on check cohomology. So since delta is an anti-derivation with respect to the cup product, the cup product induces a product in homology. So now you have a product on check homology. And, you know, and this product, well, and this cup product here on check on the check complex, you know, it is the same as the cup product in the double complex. That means this inclusion map preserves the product structure. Okay? So since the inclusion map preserves the product structure, the induced map in cohomology also does. Yeah. So now you have a product on check cohomology, and then since the inclusion map from the check complex into the double complex preserves the cup product, so does the induced map in cohomology. sometimes I use a dot to instead of the star because, well, you know, it's confusing to have too many stars. And this star corresponds to this star. Yeah. Okay. Yeah. And so what that means is that, well, we already know that I star is a linear isomorphism. So now we know that, hence I star is an algebra isomorphism. Okay. And so what do we have? So we have R star from the round cohomology to the cohomology of the double complex. And then we have I star. Well, so if you go the opposite way, it would be I star inverse that takes you to check cohomology. And so then what you get is that the round cohomology and check cohomology are isomorphic as algebras. Mhm. Okay, so this is a refinement of the check de Rham isomorphism. Okay, now we know that it's not just a linear isomorphism, but it is an algebra isomorphism. It preserves the product structure. Okay. Okay, now there's something really curious here. So let's see. Oh, I'm so glad I haven't erased the definition of the cup product on check cochains. See, if you look at this definition, you see that there's no reason why it should be commutative or graded commutative, right? Because if you switch tau and omega, yeah, then, well, so you're gonna, then you'll be looking at tau on alpha 0 to alpha r, see? And that has nothing to do with tau on alpha p to alpha p plus r, because those are two completely different open sets, you know? So this cup product is not commutative in any sense. Okay? So the cup product on the check complex is not commutative in any sense. Okay? It's not commutative, it's not anti-commutative, it's not graded commutative, because if you switch them, then, you know, they have nothing to do with each other, the two sides. But because this cup product corresponds to the wedge product under this isomorphism, and the wedge product is graded commutative. So the cup product is graded commutative on cohomology. Yeah. Yeah. So that's what's curious, that um, you know, the omega cup tall, okay, that's not equal to, say, -1 to the degree of omega degree tall of tall cup omega. But when you take the cohomology class, then you get graded commutativity. And you can see this only through the Dirac isomorphism. You know, there's no direct way to see why this is true. Yeah. Okay, so let's take a break. And then after the break, we want to generalize the definition of check cohomology to something more general abstract, you know, called Presheaves. Okay? This R bar is just an example of a Presheave. Okay? Okay, so let's take a break for 10 minutes. Okay, now, how many of you have come across Presheaves or sheaves? Can you raise your hand? Oh, yeah, quite a few. I see. Yeah. In what context? Like what courses? Algebraic geometry. Yeah, all right, good. Okay, so this is nothing new to you, but for the others, it's new. So Presheaves, they are like the Q forms of an open set, or the locally constant functions of an open set. Yeah. So in general, a Presheave on a topological space F is a function that assigns to each open set an abelian group. And abelian group f of u, okay? And to each inclusion of open sets, um, a restriction map. So let's say I going from V to U, to each inclusion of open sets, a map, okay, going in the other way, called the restriction. Um, so So you see the F could be differential forms. Okay, so yeah, whenever you have an inclusion open set, you have the restriction of differential forms, and F could be locally constant functions. Okay, okay, and then this satisfies two properties. The first is that if the inclusion is the identity, you have U included in U, then the restriction is the identity. So rho of the identity, say from U to U, is the identity map on F of U. Okay? And then rho of a composition, so if, say, W is contained in V is contained in U, okay, then rho of the composition, now let me see. So this one would be I VU, and this is I WV, right? Yeah. So rho of I VU composed with I WV. No, sorry, F. F of this composition should be F of, now this is, yeah, right, F turns the arrows around, right? So it should be F of IWV composed with F of IVU, okay? And let's write down what this means. So this means you restrict from V to W, okay? And here you restrict from U to V. And this inclusion is actually I from W into U. And so this will be rho of, you restrict from U to W. Okay? Yeah. So F of a composition is a composition, and that translates into this. Okay? That restricting from U to V and then restricting from V to W is the same as restricting from U to W, i.e. Okay? So actually, you can forget about this because we work with restrictions. And you see that the Q forms on an open set, the locally constant functions on an open set, they satisfy these properties, so they are Presheaves. Now, is there another way to say all of this using the language of categories and functors? Here, the objects are open sets in X. So to each object, you associate an abelian group. And then to each morphism, here the morphisms are inclusions, you associate, this should be a group homomorphism. Okay? And then you have these two properties. Yeah, using the language of categories in functors, what is a presheaf? Yeah, yeah. So all of this can be said in just one sentence. Okay. Yeah. A presheaf is a functor from the category of open sets and inclusions of open sets to the category of abelian groups. That's all. A presheaf on a topological space X is it's a functor that reverses the direction of arrows. So it's a contravariant functor. A presheaf is a contravariant functor from open X. That's the category of open sets in X. And then the morphisms are inclusions of open sets. That forms a category to the category of abelian groups. And group homomorphisms. So we have two examples here. The Q forms on an open set and the locally constant functions on an open set. Okay. So what is a homomorphism of presheaves? So a homomorphism from a presheaf F to another presheaf G. So is a collection of group homomorphisms, one for each U, such that, okay, so you have f of U going to G of U, and you have this f of U. And then if you have another open set V, you have an f of V here. And if V is contained in U, then you have restriction maps. And this diagram should be commutative. So Yeah. Yeah, that's what a homomorphism is, Presheaves. Now, using the language of categories and functors, what is a homomorphism of Presheaves? What is the word for, for something that satisfies this? If you have two functors, and then for each object, you have a group homomorphism, that commutes with the restriction. It's just called a natural transformation. Okay, so a homomorphism of Presheaves F and G is just a natural transformation. Now, each presheaf is a contravariant functor, so this is just a natural transformation of functors. Okay, and this is the definition of a natural transformation. Okay, now, I want to introduce another example. And it generalized this one. Okay? So instead of locally constant functions to R, you can look at locally constant functions to a group G. Let G be an abelian group. And so G bar of U is defined to be the locally constant functions say from U to G. Okay, that's a presheaf. All right, yeah. Okay, and so now we can define presheaves on an open cover. This is a presheaf on a topological space. Okay? And a presheaf on an open cover is defined in the same way, but instead of all open sets in X, you just look at open sets in the cover and their finite intersections. Okay. So presheaves. Okay. So let U be an open cover of a topological space X, and let me see, I think I always need this to be linearly ordered. Well, maybe not, no, yeah. I think it's only when I want to define the differential that I need this to be linearly ordered. So it's just an open cover. And let open U be all finite intersections of open sets in the open cover. Okay, those are the objects, and the morphisms would be inclusions of open sets. Okay. And then like a presheave on this open cover U is, okay, it's just a contravariant functor from this category to abelian groups. From with a category of abelian groups. Okay. All right, and now I would like to give you a non-trivial example of a presheave on an open cover. Yeah, so let's see. Oh, okay, so let pi be a C infinity fiber bundle with fiber F, okay? And U, a good cover of M, and then define HQ of U. So you've got the fiber bundle, and locally it's a product. HQ of U, you define it to be the cohomology of pi inverse of U. Okay, where U a finite intersection, the open set of this cover. Okay. Now, because you have a good cover, so U is diffeomorphic, not U, but because you have a good cover, yeah, so U is diffeomorphic to Rn. And we had a theorem earlier that we didn't prove, that when you have a fiber bundle over a contractible manifold, it is isomorphic to a product. So pi inverse of U is isomorphic to a product. And therefore, this is HQ of U cross F. Okay? And by the Cournith formula, um, oh, you know what? I think, yeah, I shouldn't just do Q. I should just do all of them. The cohomology of U. Okay, the direct sum of all the cohomology in various degrees. And then the Cournith formula says that this is H star U tensor with H star F. And H star U, because U is Rn, is R. And when you tensor with R, right, it just disappears. Yeah. Okay. So to every open set, you associate the same group. And yes, and this is a presheave. So this is the presheave where all the groups are the same. Okay, and that's called a locally constant presheave. Yeah, so maybe I'll just put the definition here. So let G be a group. A presheave F is locally constant with group G if for all U F of U is isomorphic to G. And for all inclusion of open sets, the restriction it goes from G to G is an isomorphism. Is a group isomorphism. Okay, so I have just introduced a locally constant presheave here, this H star. Okay, we'll stop here. And next time, we'll define check cohomology with coefficients not in R bar, but in any presheave. Okay. All right.